All right, so loop quantum gravity. It's a mouthful, right? But trust me, the ideas behind it are even wilder than the name.
What we're talking about is this, and it's going to blow your mind maybe, that space and time, like the very fabric of reality, might be more like a piece of cloth, with all these little threads woven together, than a smooth, continuous sheet.
So less like a blank canvas, more like a tapestry then.
Yeah, exactly. And to guide us through this crazy tapestry of a theory, we've got, well, it's not just any paper, it's a living review article by Carlo Rovelli. He's one of the pioneers of this whole loop quantum gravity thing.
I've heard that name before. Didn't you write a book about time a while back, 7 Brief Lessons or something?
That's the one. He's kind of a rock star in the physics world.
Well, we're lucky to have his work to guide this deep dive then. But real quick, before we get too far, for anyone who might not be familiar, what exactly is a living review? It sounds kind of intense.
So it's not like those dusty old papers you find, buried in a library somewhere. A living review, it's constantly being updated. Like as new research comes out, new discoveries, they add it in. It's like a living, breathing encyclopedia of the field.
Okay, so we're getting the inside scoop straight from the source then.
Exactly. And Rovelli, he doesn't dumb it down either. He gets into the nitty-gritty, the equations, the whole 9 yards. But the amazing thing is he's also a really good communicator. So even if you don't have a PhD in theoretical physics, you can still follow along and get the gist of what he's saying.
And trust me, it's worth getting the gist. This stuff is mind-blowing. We're talking about a theory that could completely revolutionize our understanding of the universe. I mean, black holes, the Big Bang, it's all on the table here.
No doubt. Loop quantum gravity, it doesn't shy away from the big questions. In fact, it goes right at them, like head on.
And one of the biggest questions, the one that's been driving physicists crazy for decades, is how do we reconcile general relativity and quantum mechanics? How do these two pillars of modern physics, how do they fit together?
That's the million-dollar question, right? And honestly, it's a question that's been driving physicists nuts for like a century. You see, on one hand, you've got general relativity, which is Einstein's masterpiece. It's all about gravity, how it warps space and time, this whole grand cosmic scale stuff.
Right, like planets orbiting stars, black holes bending light, those kinds of things.
Exactly. But then on the other hand, you've got quantum mechanics, which is all about the really, really tiny stuff, like atoms and the particles that make them up. And at that level, the rules are totally different. Things get weird, like particles can be in multiple places at once, information can seemingly travel faster than light, that sort of thing.
That's enough to give you a headache.
It definitely can be. But the thing is, both general relativity and quantum mechanics, they've been tested and confirmed over and over again. They work incredibly well within their own domains. The problem is when you try to combine them, try to create a unified theory of everything, everything blows up.
Everything blows up.
Metaphorically speaking, of course.
Yeah.
The math falls apart, you get infinities popping up everywhere. It doesn't make sense.
So it's like trying to fit a square peg into a round hole.
It's a perfect analogy. And for a long time, physicists have been trying to find a way to either reshape that peg or maybe stretch that hole a bit. But loop quantum gravity, it comes along and says, hey, maybe, just maybe, we've been thinking about this whole thing wrong.
Oh, how so?
Well, it's like this. See? Imagine you're watching a play. You've got actors on a stage, and they're following a script. Most attempts to unify physics have been trying to figure out the ultimate script, the laws of physics that govern everything.
Makes sense.
But loop quantum gravity, it comes along and it says, but what about the stage itself?
The stage?
Yeah, like what if the stage isn't just this fixed, unchanging background? What if it's dynamic? What if it's part of the play itself?
I think I see where you're going with this. You're saying space-time itself, the very stage on which the drama of the universe unfolds, could be more complex than we thought.
Exactly. And that's where loop quantum gravity comes in. It says that space-time isn't this smooth, continuous background that Einstein envisioned. Instead, it's woven together from these tiny loops of, get this, gravitational force.
Woven from loops.
Yeah, you got it, loops. And these loops, they're not just some abstract mathematical concept. They're the fundamental building blocks of reality itself. They are space-time.
Loops, huh? So we're not talking about strings anymore, like in string theory. I thought those were all the rage in physics circles.
Ugh, string theory. Yeah, you're right. It's definitely got its share of the spotlight. And actually, both loop quantum gravity and string theory, they're both gunning for that title of theory of everything, trying to explain, well, everything.
A real clash of the titans then. But in this corner, we've got loops, and over there, it's strings. What's the main difference? Is it just a matter of shape?
Well, on the surface, it might seem that way, right? Loops versus strings, but it's more than just shapes. It's about how these theories see the very foundation of reality. See, string theory, elegant as it is, it kind of cheats a little.
Cheats. Tell me more. I'm all about exposing academic dishonesty.
I wouldn't go that far. But string theory, it relies on this pre-existing background space-time. It's like, imagine you're setting up a stage for a play, right? String theory comes along and says, okay, we need a stage already built. Then we can have our actors, these tiny little vibrating strings, doing their thing on that stage.
So it's assuming the stage is already there, that space-time is a given.
Exactly. And that's where loop quantum gravity goes, hold on a second. Why do we assume the stage is just there? What if the stage itself is built from those tiny loops we were talking about?
So loop quantum gravity doesn't need a pre-built stage. It makes its own as it goes.
You got it. It's what we call background independent, which sounds really jargony, but it's a really powerful idea. It means that space-time itself isn't some fixed external thing. It emerges from the interactions of those loops.
That's pretty radical. So are you saying loop quantum gravity is more in line with Einstein's whole general relativity deal than string theory is? Since general relativity was all about space-time being dynamic, right?
You're definitely picking up on the key points here. Loop quantum gravity really takes that dynamic space-time idea and runs with it. And because it dives right into the Planck scale, that's like the smallest possible scale, way down where quantum effects of gravity would be strongest.
Planck scale, right. That was, what, 10 to the minus 35 meters, something crazy small like that.
Yeah, something like that. We're talking crazy small. But the point is, at that scale, loop quantum gravity could potentially explain things that really stump string theory, like what happens at the singularity of a black hole.
Oh, black holes. Those things are like the cosmic vacuum cleaners, just sucking up everything around them. Even light can't escape.
And at the center of a black hole, according to general relativity at least, is a singularity, a point of infinite density. It's a place where the laws of physics as we know them just break down.
And string theory struggles with that.
It does, because it relies on that pre-existing space-time, right? When space-time itself collapses at a singularity, string theory doesn't have much to say.
But loop quantum gravity, with its self-made space-time, might have an answer.
It might, and that's just one of the things that makes it so darn interesting. But hold on, before we get too carried away, gotta be upfront here. Loop quantum gravity isn't all sunshine and roses. It has its own set of challenges, just like any theory trying to unify physics.
Right, there's got to be a catch. Come on, spill the beans. What are the downsides?
One of the big ones is connecting it back to what we see in the lab, to the everyday world of particles and forces that we understand pretty well. Like, how do those loops, those tiny chunks of space-time, how do they give rise to, say, an electron or the electromagnetic force?
So it's like having a blueprint for a house, but not knowing how to actually build the thing or what materials to use.
That's a great way to put it. We've got this incredible framework for how space-time itself might work at the most fundamental level, but translating that to the physics we can actually observe and measure, that's still a work in progress.
Okay, so that's one challenge. What else?
Well, there's also the fact that, and this might surprise you, but there are actually several different versions of loop quantum gravity out there.
Wait, seriously, I thought it was just one theory.
You wish. Nope. There are different camps, each with their own take on how those loops interact, how space-time evolves, all that good stuff.
So it's kind of like, what, different schools of thought within loop quantum gravity, like Chicago School versus the Austrian School of Economics or something?
Something like that. And just like with any good academic debate, there's healthy disagreement about which approach is the most promising, and it's all still unfolding, which is part of the excitement, right?
Definitely. Always more to discover. But even with these challenges, different versions and all that, loop quantum gravity has already achieved some pretty remarkable things. Rovelli talks about this idea that space itself is quantized. What does that even mean?
It's one of the most mind-blowing consequences of the theory, honestly. See, in classical physics, we think of space as being continuous, right? You can keep dividing it up into smaller and smaller pieces infinitely.
Right, like zooming in on a map. You can keep going and going, at least in theory.
Exactly. But loop quantum gravity says, nope, there's a limit. It's kind of like those old video games, you know, where everything was made of pixels. You zoom in close enough and it's all blocky.
Yeah, like that old Super Mario Bros.
Yeah.
On the original Nintendo.
Exactly. Loop quantum gravity says space-time has a pixel size too. It's the smallest possible unit of area, this fundamental graininess to the fabric of reality. And just like you can't have half a pixel on your computer screen, you can't have half a unit of area in loop quantum gravity.
So there's a limit to how small things can get. A fundamental limit to divisibility.
That's the crazy thing. And that has huge implications, not just for black holes, but for the Big Bang, for our understanding of how the universe began. It's wild stuff.
So you're saying black holes aren't actually empty, that there's actually something there at the core?
Well, not empty exactly. Think of it this way. You see that black hole on that poster over there, the one swallowing that poor, unsuspecting star?
Yeah, brutal way to go.
Totally. But we tend to picture black holes as these, like, Smooth, featureless voids, right? Just pure empty darkness.
Because that's what it looks like from the outside, right?
Right.
Like even light can't escape that intense gravity, so all we see is black.
Exactly. But loop quantum gravity, it gives us a way to peek behind the curtain, so to speak. It says that zoom in close enough down to the Planck scale, and a black hole is actually a teeming, bubbling sea of loops.
Loops again, huh? So those things are everywhere. But how can loops explain, all the crazy stuff that's happening inside a black hole?
Well, those loops, those quanta spacetime, they're not just sitting still. They're constantly interacting, merging, changing. And it's those interactions, that intricate dance of loops that gives a black hole its entropy.
Hold up. Entropy. Didn't we talk about that back when we did that deep dive on thermodynamics? That was a wild one.
We sure did. But it's popping up again, and that's the beauty of physics. Everything's connected. See, in the case of a black hole, entropy is a measure of all the possible microstates. Basically, all the different ways you can arrange the quantum building blocks of the black hole, those loops, and still have it look the same from the outside. And because of that Planck scale graininess, those quantized chunks of space-time, well, there are a lot of possible arrangements.
Okay, so more ways to arrange things means more entropy. Makes sense. But how does loop quantum gravity actually describe those arrangements, those microstates? Like, do physicists actually sit down and count loops?
That would be a pretty tedious job, right? Counting infinite loops. Thankfully, there are more elegant mathematical tools for that. But one of the big ones, and this is where things get really interesting, is the Hamiltonian constraint.
Okay, the Hamiltonian what now? Sound like we're diving into the deep end of the theoretical pool here.
We might need a bigger pool. But don't worry, we'll take it slow. So the Hamiltonian constraint, it's kind of like, okay, imagine loop quantum gravity gives us this incredible snapshot, right? A frozen picture of space-time made up of all these loops.
Okay, I'm picturing it.
Beautiful. Now, the Hamiltonian constraint, it's trying to figure out the rules, the dynamics of how that picture changes over time, how those loops actually interact and evolve.
So if loop quantum gravity gives us the what of space-time, the Hamiltonian constraint gives us the how.
Nailed it. It's like if loop quantum gravity is the clock itself, all the gears and springs and whatnot.
The Hamiltonian constraint is the instruction manual.
Exactly. It's telling us how those gears turn, how the hands move, all those intricate mechanics that make the clock tick.
And has anyone figured out those mechanics yet? Or are we still waiting for someone to crack the code?
That's the million-dollar question. And the answer, well, it's complicated. There are different approaches, different ways of formulating the Hamiltonian constraint, and each one has its own strengths and weaknesses. It's still a very active area of research.
So more like a choose-your-own-adventure novel than a straightforward textbook.
Exactly. And one of the most intriguing paths in that choose-your-own-adventure story is something called spin foams.
Spin foams. I'm not even going to try and picture that. What in the world is a spin foam?
Okay, so imagine this. We're zooming in on space-time right down to the Planck scale, watching those loops evolve over time. What we might see is something like a constantly shifting, morphing foam of interconnected bubbles.
Bubbles. We've gone from loops to bubbles now. My brain is starting to hurt.
I know, right? It's a lot to wrap your head around. But stick with me here. Each of these bubbles, it represents a quantum of volume, like a fundamental chunk of space. And as these bubbles interact, they merge and combine. They create a kind of dynamic, ever-changing history of space-time. And that's a spin foam.
So are these spin foams, are they like those computer simulations of the early universe? The ones you see with all those filaments and structures forming?
You're good at this. That's a great way to think about it. But in this case, it's not just matter and energy that are evolving. It's space-time itself, constantly changing, bubbling, rearranging.
Wow. So it's like we're watching the universe knit itself together one Planck length at a time.
That's a beautiful way to put it. And that's the beauty of loop quantum gravity, you know?
Yeah.
It's not just some abstract mathematical theory. It's giving us this radically new way of understanding the universe, the very fabric of reality.
It's definitely given us a lot to think about.
Yeah.
But we've only just scratched the surface here, haven't we? There's still so much to explore when it comes to loop quantum gravity.
Oh, absolutely. And that's part of what makes it so exciting, right? It's a theory that's still being written, still being explored. And who knows what incredible discoveries await us as we delve deeper into this world of loops, spin foams, and quantized spacetime.
Well, to our listeners out there, if your curiosity is piqued, and how could it not be, I encourage you to check out Carlo Rovelli's work. His Living Review article is a great place to start, even if some of the math might make your head spin a little.
And don't forget, science isn't a spectator sport. It's something we've talked about today, sparked your imagination. Go out there and explore, ask your own questions, and maybe even make some discoveries of your own.
That's what it's all about. Until next time, thanks for joining us for this incredible journey into the mind-blowing world of loop quantum gravity.